Welcome to ASCII Geek.
Hey, if we haven't met already, I'm the digital avatar of ASCII Geek,
where we build your next advantage with tomorrow's technology. And today, one of our experts is stepping in to show our latest breakthrough. Enjoy and happy learning.
All right. 50 pages of dense corporate indemnification, rapidly scanned and fully ingested by the system in less than 3 seconds. And almost as soon as the file lands on the drive, an artificial intelligence flags 3 highly specific liability traps buried in subsection G. The engine isolates the exact clauses exposing the company to financial ruin with clinical precision. Curious, analytical tone. Processing a contract this complex requires immense computational reasoning, but uploading classified legal documents to an external server is a severe compliance violation. So how did this system execute a deep context audit without a single byte of data ever leaving the building? The answer requires stepping entirely outside the traditional web browser. Large language models possess the cognitive capability to parse complex legalese, but routing that data through a standard web interface reduces your operational security to 0. Every time a user pastes proprietary information into a browser-based prompt, that text becomes vulnerable to external cloud training vectors. To secure the data, we move the LLM to a terminal-level execution. Instead of pinging a remote server, the intelligence is tethered to an isolated local directory. We call this restricted computing environment a closed-circuit sandbox. By stripping away the chat window and migrating the model directly into your file system, you discard the generic chatbot and build a secure, deterministic Audit engine. This localized isolation is the absolute prerequisite for processing classified legal documents without breaching strict corporate data protocols. To see how this engine actually runs, we have to look beneath the interface and examine the exact file structure making the decisions. If you simply hand an LLM a contract and ask it to find errors, the results will be unpredictable. Open-ended natural language prompting is too ambiguous for rigorous legal work. We have to constrain the model's inherently probabilistic nature. We do this using a specific directory structure, known as the DBS Framework. The architecture relies on 3 interconnected pillars: direction, blueprints, and solutions. An unconstrained AI simply guesses the next word based on a prompt. By routing it through these 3 nodes, we force the AI to operate as an autonomous, rule-bound operating system. The first node establishes the rules of engagement. We call this the direction layer. Physically, this is a stark, monospace markdown document titled skill.md. This single file acts as the authoritative manager for the entire local directory. At the top, a metadata section dictates strict logic constraints. It tells the system precisely which triggers authorize an audit, preventing the AI from activating on the wrong files. Below that, a workflow code block maps out a rigid order of operations. The model is commanded to ingest the full text first, hold it in context, and only then begin scanning for indemnification risks. This pre-execution check ensures the model follows the mandated legal procedure without exception, eliminating random behavior. The second node accesses the system's permanent memory, blueprints. This is a dedicated folder labeled References, loaded with static proprietary compliance guidelines. A language model trained on the open internet has no concept of a specific company's internal risk tolerance. Generalized legal data is useless here, so we mandate a direct comparison. The AI evaluates the raw contract exclusively against the pristine golden record. By tethering the analysis to this exact text, we eliminate hallucinations. It only flags language breaking the predefined structural mold. The audit's accuracy is derived strictly from approved internal precedent, not generalized AI guessing. The final node provides the functional hands of the operation, solutions. Language models are built to predict text, which makes them inherently unreliable at executing precise mathematical calculations and deterministic data extraction. To fix this, we use a scripts folder containing executable Python files, engineered specifically for hard logic tasks. If the contract requires calculating a liability cap from multiple variables, the system doesn't ask the LLM to guess. Instead, the manager pauses language processing, triggers the Python script, and ingests the hard data back into the workflow. This handoff mechanism bypasses the model's flaws by delegating required logic to deterministic code. Solutions provide the absolute mathematical certainty that natural language models alone can never guarantee. Pulling back from the directory level, the architecture surfaces its final result: a clean, highly formatted report detailing exact vulnerability metrics and isolating the critical risks. The physical data was ingested, constrained by the direction layer, analyzed against the blueprints, and mathematically verified by the solutions. And this entire multi-step analytical process executed in milliseconds. Most importantly, not a single byte of proprietary contract data ever touched an external cloud server. The local sandbox simply returns to a quiet standby mode, waiting autonomously for the next highly classified document. Professional efficiency now relies on building dedicated, closed-circuit AI operating systems on local hardware.
All right, that's the update from the lab for today. I hope you learned something new. Head over to ASCIIgeek.com